just the bell,
Oh, okay.
so that I can give you some stuff to read and so on.
Thank you very much.
Không, Thế Huy làm hợp á, Thế Huy hợp với thầy á.
học từ tống cho tới tốt luôn đó bà.
Sao? Được nghe nói Đà Lạt, yêu Hà Lan mình làm từ Sài Gòn lên.
Ủa mình không có học cao tốc đó anh.
All right, so I was here, I wanted to tell you, you are going.
Yeah, we would like to.
Mình không biết được mình đi cô vẫn ngủ. Thì tức là đi lang thang phải không anh? Anh đọc bằng tiền không? Phải nhẹ thôi chứ. Đúng rồi. Anh nghĩ là có anh nghĩ là rất thôi. Không có nói gì hết luôn.
So? Oh, he didn't come. So let's wait Look, I was here telling you that why is it important to scale the data? Well, scaling is the meaning. If you have a variable x, you sort of want to demean it, and then divide by the sum. So that's a standardization. Standardization is sort of important because it makes these to have the same scale, in the features, x1, x2, x3. To have the same sort of scale, the same mean, and so on and so forth. If you don't, for example, let's say here we have time, and time is from 0 to 6,000. Alright. And one of these will be 6,000, or 5,000, or 1,000 somewhere. It will be a very big number. So let's say this is time. And then let's say this is volatility, it will be 1, 2, 3, small number. And that is the market excess return is also very small. 2-3% or so. That's not big. That will be 2, this is like 1, 2, but this is 1,000. So then what happens is that this optimizer that we have later, we have a problem with getting this weight. So there's a balance. Right? So it needs to actually choose a very small weight here. So if it is 10 to the power of 3, then the base if here is 2, then it should be 10 to the power of plus 3, minus 3. So it should be very small. Right? So that will be a little problematic oftentimes. And as such, then whenever one has, you can do the optimization, it doesn't matter. You don't need to do scale them. Right? Well, sort of make them like so. But oftentimes that helps with getting a better estimate here, right, with these basic requirements. So we keep in mind, I mean, I'm saying this because if I transform them, then later if I want to get a derivative, then I have to remember, I try to scale them and I scale back. That's sort of what we need to keep in mind. That's just the standard, the denominator. So the sigma x that we have. Right? So, but I mean, that's in any case, so here I will have the time and I will scale it first. Right? So it is not very large. And that is the f, a, and n. So we just divide it by the maximum value. And so it's not a number from 0 to 6,000, but it's a number from 0 to 1. Well, it's still the time track, right? But with a smaller scale. Right? So that's why I do this. So that will be the f, a, and n. Time, you can try to see whether there is a difference every. So time dot max. So divide by the max. So it's sort of the scale time with at this DFA and N just to see what is in there. Alright? So that is the asset excess, this is the market excess, this is the volatility, this is time, and this is the scale version. And the volatility, we have a window of 20, so it means that for the first 20 observations, then there is none. Right? Because say if I'm at day 2, then there is no 20 observations before, it's just one. Alright? So then this generates a none. So these nuns we have to drop. Okay, so before going on, and getting rid essentially of the stuff. So here, when we simply drop them, so we say df underline n or drop now. Axis should be 0, so row-wise we want to do that, and then in place should be true. Okay, so we just drop the first observations and then we are good to go. Right. So now we need, so this is our data frame, so we have the data and so on and so forth, but then now we need to know what are our features. Right, so features are the explanatory verbs. They are in data science called features. I call them features. So features are what? So they are the market excess return, market excess return, so that's the feature number 1. We have the volatility, which is the rolling volatility that we have, and then we have the time scale. Right, so these are the features as we have them. So features are here, so they are just the names. Right. Now let's define, say, the A and N, the values that they go into this table. So these are the names, and now I'm defining the vector x. Alright? So this vector x, which is going in my as inputs, right? Inputs of the network. Okay. And that would look like so. So you go to the df a and n, and then bring the features. Okay, so that is what we have. And then here we get the values. Okay, so that's a very important, basically, little bit. All right. So the MLP regressive does not work with data frame, right? But needs arrays. So we get the values so that we have normal vector of a lot of data frame, but obviously we need the values. So we get the values. Okay, so here then I have the values that they go in this ALN. Right? Now, if you remember, so I told you that we generally do the scaling. Well, I mean, you can't do the scaling in whatever rate, calculate the mean one by one, right? But then we can actually, so if you remember, so we brought in this standard scalar, all right? So let's define it as so. So that's the scalar that we have. And then here I would say x scaling are the scalar. So that's the standard scalar as we have. And then here we fit transform. Alright, so that's the needs and when it takes things, divides them by the standard. Okay. Good. I mean, that's sort of, I mean, there are a lot of wrappers, there are a lot of functions, which oftentimes you don't need them. But then if you remember them and you know them, then they become very handy and make you very fast in programming. The problem is that there are so many. Yeah. So sometimes I remember, sometimes I don't. Right. If I don't, then I write my own function. Alright, so that's sort of the issue. But then the important ones, the bigger ones like the trading step, then you need to know. Alright, so that's sort of doable. And the things that then one is say 90 years of age when you're very old, then you know everything. The problem is that you don't remember them. So then this is the thing that you use them and then you learn them, and then you forget point is that the scaling is important, right? So that's sort of what I wanted that you see. Remember, and that is for alleviation of the job that this optimizer has. That is important. So now we are ready to go and then define our ANA and train the neural network. All right. So let's actually go on with. So I just want to sort of ask you a question. If I don't have a hidden layer, no hidden layer, yeah, nothing. So it means that so there is none. So that will be the output of the regression. All right. Then it becomes what? Output of the network. Say, let me draw it so that you know what I mean. Okay. So let's say we do not add any layer. Nothing. Right, so. Yes. You have a question? I will ask the question. So
No, I mean, if we don't have, it becomes like regression.
that's true. That becomes a simple regression. So if there is no layer, then you are back to the simple regression exactly. So you answer the question. So if I don't have anything and this is the only node which I have afterwards, it will be a linear combination plus a bias. So it's a simple linear regression. So you can do OLS, but that will be OLS. The minimization. That's least squares. Yes. With no hidden layer, then will be a simple regression. Okay? But we don't do this. But you keep it in mind. No hidden layer means simple regression. It's linear function. Then the more layers you add, the more you go away from this linearity, and then the more nonlinearities you can take into. Then I don't need to write. Very nice. So let's go on with sort of defining the model. All right. So the model that I have, so we bring in the MLP regressor, and then it takes like many things, right? So let's start with the hidden layer sizes. All right. So here we pass a topic. All right. So the default is 100. So here, well, that's the default. All right. The default hidden layer, because that's a topic. If I say 100, then there will be just the size will be 1. There will be one layer with 100 neurons. Okay. But if I basically add more dimensions to this, for example, let's say we use, what do you want? Say 3 and 2. Alright, so later we make it a bit better. Alright. So the other function that we have is the activation. So, and then the activation by default is, well, that's the rectified linear function, so ReLU, which is 0, and then it becomes like so. Right? So this is this function. So when it is positive, then the effect is rectified. Linear, so let's select rectified linear activation. So that is called ReLU. Right? That's also the default, so I did the same with the default. And as I said, ReLU with enough layers and enough sort of neurons, then it will be well good enough to capture any dynamics that one has. So sort of the nonlinearity is not that. Well, then we need a solver. All right. The solver, I will choose Adam. So Adam will be the guy who will solve this for us. That's an algorithm. Yeah. And then, so well, let's fix the max iterations. Right. So let's set it to 5,000. Right. And well, there is also a random state. All right. Let's set it to 42. All right. So. It's a little bit hard to tell you what these parameters are, okay? And without telling you how the optimizer works. This max iteration you understand. So that's sort of the maximum number of iterations, because that's a linear numerical optimization method, this one. Then you need to sort of restrict the number of iterations, and that is 1,000. Let this 42 be as is. You can read on yourself what are those guys. And of course there are other things. So, for example, let's say there is a batch size. Alright? This is saying you have 6,000 observations, and then it takes some of these observations, alright, so those are training on them, so little by little, so like periods, sort of little by little takes, so not one by one, but rather takes batches. Alright, so that would be, that is something that makes it a little bit faster. Alright. This is the so that's max function, so this is the number of the iteration, sort of the values that you have, there is a tolerance. Max iteration is 200 by E4 that I increased it. That's the learning rate. You know the learning rate? So that's the dimension, sort of, you know Newton-Raphson, right? Newton-Raphson? We find new persons, so sort of, you should have learned it in some of your previous classes. Right, so let's say you have a function and then you want to find its roots. The root is here. Then you start at a point, right? And then, so the Newton actually says, okay, let's do like so. So sort of at this point you draw a tangent, and then you find another point. And then you go there, and then you draw another point. So do this tangent, and so on and so forth, right? So to speak, the steps that one takes are clear. So you know how much you sort of move. And then you move and so on and so forth till you come as close as possible to something where the value of the function is zero. Right? So then, there's also other methods when it comes to saying that's a root finding first. So then you have the first order conditions and you want the roots, then you use that. Right? But then there's also, say, well, let's say you are after this minimum. Right? So that's a function, I want the minimum. Then I can write the first order condition and find the Newton-Raphson. Or I can actually start from one point, right? So that's what I have. And then say I start at this point, so that's the starting point. Right? So the slope is negative, it means I should go to the right. So then I come to the median. Okay? But how much do I go to the right? That's true, but I have to take one step, one little step. Let's say I go from x0 to x1. How much do I go? I should go a negative line. Alright? If the slope is higher, then I go more, because I'm sort of, so if the slope is less, then I go less. Alright? So let's say I'm here, then I have the slope, some number, say -1. Right? And then if I want to go here, then I have the derivative. X0 times something, some little thing. Right? So that is called the learning rate. How much should I move to the right and to the left? Alright. So how much of the derivative? The derivative is negative. So we don't go fully the whole derivative to the left. Or rather multiply by some little thing. So we learn how much should we go to the left or to the right. Proportional to this derivative. And that's the learning rate. Right. That's what we call it learning rate. Yes. We learn how much we should move. Right. And this learning rate is this. Where is it? Like 10 to the power -3. Right. So that's sort of, so I mean that's not one dimensional, this is sort of a very big in the vector, and then how much we go to the left and to the right. I leave the rest. Alright, you check them for yourself, okay? And really, so the simple implementation really need work, and that's good enough for our ED purposes. So now this is the model. Alright, so let's add the model. And let's do a fit. So we say model, we just fit it to, well here we have x scale. So that's the features that we have. On the right hand side, then we have EFN, where that's the response, and that is the asset excess. So it will take some time, and then we are good. Okay. Now, before I actually start calculating the cap EBITDA, alright, and so on and so forth, I will close the function online, and then you use it. So that is somehow, it will take long to program it and tell you the details, so that will be quite time consuming. But that's a beautiful function. I will put it in the Python programs. You don't see. I'll put it here in courses and there in the Python program for the classroom. This will function MA. Please download it. I will do this. So that's a function. When you take this function, which you just uploaded, you found it. Then we go in our program and bring it here. That's where the function that we want. Alright. Alright, so that's sort of from the model. It takes the model, and you can also add it takes the model that we have fit. Alright. And then you can also add the feature names and then sort of very nice nicely, sort of shows you what is I mean, how does actually this guy looks like, alright? So for that, then we say, so what is the name? So I have actually two. That is the nice name. So here I would say after that, so I will pass the model to it, and then the feature names, let it be the features. I think I call it features, right? This. Feature name is equal to features. Alright. Right, let me make it a bit smaller so that you see the scale. What is going on. So that's the function that starts from here. And well, so that's now we make it bigger. I just wanted to that you see. The function that starts there actually gets the structure of the model. Right? It's actually very nice if you take a look at this function carefully. Just to see, so how do I extract the architecture from the model? So these are all the properties that you can read them, and then use them in sort of this setup to see everything. So I will, sorry, there was a comment on features and feature, something. I think it's correct, no? It's called features. It was wrong there. Now I can make it bigger, right? So after I fit the model .fit, then this function I have and I call it. I call the function. And that's the flow. And that generates this picture for you. Alright, so this one, right? So that's such a nice one. Okay. Do you have the same picture? Just one that you have it. And yours also work? That's what it takes some time. You have it too? So this is defined in here. So this is called row MLP2. That's the name of the function. This is what it is. Take a copy. Just like that. And then go down. And then here we remove. And then double dot and remove. And then the feature names is equal to features. Because we call, so features is a list which includes the feature names. Equals features. Just features. Now if you run the function, you have not defined. Then you haven't, let's go up. So here is the model. Let's run this part. Yeah. Right. Let's look very well and define the features. The features we have market excel and time scale. So the model fit work, right? from the previous file, right?
Yes.
And maybe you should run it all. These people will be removed. And if you want to run it all, then you can press the play. And then this you should also remove. There was another mistake here. So there is no red dot here, as you see, but there is another one. You can click on the red. So the previous one, yeah? And let's see what is the error. Let's go on the red dot. It says invalid sequence. I see the problem. Yeah. So this would be date, time, with forgotten the function. So use Brilliant. Record. You have installed that. Where is another one? Maybe you can this QRT underscore. No, here you should do. No, SQRT. No, you see complaining. Says, forgot, forgot a comma. Here. So beta times, this should go on. You should do it one by one. I don't know what is going on. So that's sort of. No, but actually, this is from the previous code. No? But do you have it? Such nice one. You fine? You're happy? So we needed that function. Okay, now more or less you have it. So let's look, what does this graph tell you? That's the network structure. Three inputs, two hidden layers, dimensions 2, dimensions 3. Remember we chose 3 and 2. And y is the output. Alright. And out there then we have hidden layer, we have 3 nodes. The function is ReLU, that's ReLU. Here is also ReLU, and here is IDENT. That's a reference. The beginning also the activation function is IDENT. So these are our saved messages. So sort of in this moment, and then we can read them and then put them. Okay. Now here are the names of the variables of market excess return. That's the volatility, and that's the time escape. Now these lines are either very thick or very small, right? So sort of thin. So these are chosen in the program depending on the weights. So when the weight is bigger, you will see it. So then the sort of line becomes a little bit. So that's the thickness of the line. Right? And they are either green or red. Green is when the weight is positive. Red is when the line, when the weight is negative. Right? Now let's look at the market excess return. So it has a direct. So the first one that we have is positive, and that's thick. Right? So they're relatively big weights compared to others. And well, I mean, then there is this neuron. So sort of when this neuron actually collects these ones linearly, then takes market scale positively, time scale positively, and then market excess positively, and negatively they go back there, and positively they go out. But what you notice, if you look at this, it looks like that market excess return has different channels that can affect Y. So the one which is sort of looks like it's not really direct, right? So that's the first one, it's green and very big. So and then the effect of market excess return on that then comes from the first, from the second, from the third, and so on and so forth. So there are basically many ways market excess return actually goes and then happens to affect Y. Right? So but that's sort of the market structure. The weights are there, the biases are over there, so we can read them and then plot them and so on and so forth. I could even add the values on the edges, but that would have been very long. Alright, so that's sort of what we have. And these layers are very few. Right? Let's maybe add a bit more to them, and then sort of see how the sort of this actually structure will look like. We just want to play a little bit around with the model. Now that we are here, we can do more. Let's define, so after this, at the very end, so we define a model 2, all right? There are hidden layers, or let's say 20, and then here 10. So there will be here 10 and 20, 10 and 20 there. So that's model 2, okay? And let's do the drawing again. So with model 2. We have to fit the model. So let's sort of, I need that too. So now that we define the model, then we do a fit. So that's model 2 fit. Okay. And then the coefficients will appear. And that is the new one. With 20 and 10. Alright. That becomes pretty big. So that's the structure. We have 3 inputs, and then here we have ReLU. Maybe the title we should remove. Some are very ugly, so I'll mix it with the others. So here we have 20, and then there are 10, and then there is an output. So that's sort of what we have. It becomes a little bit more. So if there is any nonlinearity, probably this will capture it very well. Good? So what we did was that we linked Y to the input variables, these 3. Alright? But what we needed was this derivative. which we can go find. Alright? We can go find it and then plot. Alright, so which is actually not a big deal. The only thing that we need is to fit essentially or predict the output with different basically values. The true values and values where the market excess return is changed by epsilon. Alright? Then we will have a difference divided by epsilon, and that will basically give us the derivative which we can plot. Right? So that's what I will do now. And next. Okay. Alright, so well we can do it with both models just to see how it differs the first. And remember that we scale x. So if I want the beta, then I have to unscale. So multiply by this scale. Right? So let's maybe call it sig of let's call it sig here. And that will be well df a and n. We have market excess, right? Not the standard deviation. Okay, so we just need it sort of for our further analysis. Right? Wait, if you add another layer, say 5, let's do it, and I'm interested to see how it will. If you have 3 layers, then you'll have the other layers too. So I have here 20, 10, and 5. That was this. Alright, so that's the standard deviation which I need. Now let's go on and then calculate the derivative. So Uber lim and Uber 3. Yes, then I mixed you with water. I will post this code online and you take it because I see that maybe you are struggling with this. Oh, okay. You don't need my code then. I will post it then like today in the evening online so you have it maybe. Well, let's define then some epsilon. So I want to go and then get the derivative. Obtain the derivative. Right, so let's define some epsilon to be 10 to the power minus 4. Yeah, so it's a very small number. I mean, what I'm actually doing here is that I'm saying that this is almost equal to f of x1 plus 10 to the power minus 4, x2 and x3 minus f of x1, x2 and x3. So because we have to let epsilon go to 0, divided by epsilon, which is 10 to the power minus 2. So, well, I mean, the first one I change the symmetry, and then, well, calculate this the sort of ratio. Okay? So that's what I'm doing. So that's epsilon, and then let's say here we say that we have a perturbed x, which is, well, let's take a copy, so a hard copy. What did I call them? X is k, so that's the features, so they go in this, let's call them that. And now I need just, well, the first one was the market excess return, right? So let's take the copy first, the hard copy. Alright. So now x perturbed, that's a small perturbation. That will be, we say, alright, so moving all of the rows from the first column whatever they are, the epsilon. Yeah, so I mean the first basic requirement, I move a little bit by a little epsilon and make it bigger. Okay. Now that we have that, now that we are here, then let's say we have by the predicted values, so by half. Alright, so I'm now calculating without the perturbation, essentially. So I would say model dot predict and at x scale. Alright, so here then we have y hat with the perturbation. It will be model, or model 2, because that's the model which is bigger, has more neurons. Here again dot predict and x underline perturb. So I have now all. That's my epsilon, this is my perturbation. First there is a copy. The first column I move by infinitesimal amount. I do the fits before perturbation, after the perturbation, and now I can get the n, which is very simple. That will be y hat perturbed minus y hat divided by x. Right? But then remember that we scaled it with sigma, so we now multiply by sigma. So you understand what I'm doing here? Yes. That was clear. Very good. Let's simply do this. So let's see. So that's the derivative. And then a scale back. So let's plot. Just to see how it looks like. Alright. So let's say PLT dot plot. So that's the df ANN dot index. I remember. Let's look at df ANN. Well, that has a nice index. Alright. And df. Oh, let's add this to the df ANN. df ANN beta of ANN is beta ANN. Okay. So now we can go plot that. Beta ANN. Okay. And PLT dot show without much going up and down. PLT dot create. What is it? Key error. Oh, df underline ANN. Right. That's a very nice graph. Right. So I'm actually going back to the very beginning, right? So then we started talking, okay, so does it actually, is it a good model or not? So the thing is that with fitting, or linking the y, axis to y, it's good. It does actually a very nice job. Alright. So we get actually sort of the non-linearities that one has here. Okay. But I mean the fact that I have to go calculate the derivative of this function, right? So that's subject to a lot of numerical errors because that's a very big function. Right? And you may get actually betas which are sort of not really known. So now we have to start tinkering a little bit. Maybe changing the layers. Right? So maybe instead of 2 then we use 3. Instead of 20 we use 100. Right? So we have to play around. And to this date, there is not much that one can actually do with choosing the number of layers and the dimension optimal. One doesn't know how to do that. I mean, you can play around with that. So if I now change this, now let's say we go to the model and then we start doing it. Let's go with the simpler model. Okay. So instead of model 2, then I will say simply model 1. So that is the one of the model where we have just 2 layers with 3 and 2. Alright. Then I get something which is more problematic. So it goes up and down a lot. And that's not nice. So maybe the number of, so this one is better compared to the other one. So maybe I have to increase the layers. So instead of 20, you use 100. And so do you want to try? Well, let's do that. Let's have a model 3 where we have more of these. Model 3. Let's say here I say 100 and say 50 and 20. So this I can take off. That's model 2, and then we can also throw model 3. Just to see how it looks like, it will be very, very different. Okay. Probably there will be not much to see. That takes also, look, this is the network, right? So 100, 50, and 20. Maybe I should change this so that they are not going on top of each other, but it doesn't matter for now. And let's do that with model 3. Just to see what happens. Okay. So somehow it looks like that it at least gets the pattern which we got non-parametrically and in a rolling window stuff, right? So the beta was small and then afterwards was going up, right? And also remember, back then when we didn't have volatility and time. Right? So they were not in our bush, right? So, but here they are. They're not directly comparable, but what I see here is that if I increase the layers, means that I increase the complexity. And remember NVIDIA, so first beta was small, it was going high, right? So around probably time. So this somehow again comes down, and then recently then it's again high, right? So more or less, it seems that it captures what we already knew, what we can relate to, you know, what we can understand from the theories that we have in finance, right? So whether this is a good actually Kaplan beta or not, I actually somehow doubt that it's a good one. So well, it is capable of capturing a lot of this stuff. So maybe we could do this regression with more relevant factors, not time and volatility, but rather we could do maybe better stuff here, add more relevant features, right? So I'm going back to finance theory, right? So financial actually theory says, okay, market access return, and then Farmer French actually brings some other variables. Maybe we have to bring them in, and that will make this better. But at the same time, it also makes the CAPM regression better. So, well, I mean, if you sort of look in the literature, right, you never, well, rarely you find somebody estimated CAPM beta this way. They always stay with the theoretical results. So if you have a strong theory, then you stay with it. You don't need to deviate. You make it a little better, by including maybe more variables. We don't need a big hammer. So you can indeed use that. It's okay. So that's sort of what we have in general. Well, as I said, so I'm not saying that this is not a good model, all right? I just took this example so that I tell you it is what it is, how to implement that, all right? So now you can. Now you can. It's sort of 2 hours ago you didn't know what is MLP, what are neural networks, but now you know. All right? With this implementation, you can do a little more reading with your sort of on your own. But I just want to give you a little bit of caution, all right? That maybe one doesn't need to go away from a model which is established. People may not like. Maybe it's about the capability. But then on the other hand, so if you have, say, a task which is a investment, all right? So CAPM is generally used sort of so that you identify some assets that are more risky or less risky, sort of screening, right? So you can use it to screen some of the assets. So if you want a portfolio that is very risky, then you go and then use that they have a higher risk. Right? If you want something that has less risk, maybe you can go and focus more on those that they have a small stable beta. Right? And in that sense, then it somehow seems to be alright. So sometimes it has been low and then sometimes it has been high. Right? All in all, this tells us that NVIDIA is risky, which we knew before doing this. We know. Oh, that is also off.
No, it's on. It's not. Keep it as a cat.
This is like a child that you take the ice cream off it. Sorry, I just didn't realize. Okay, so are you happy with this level of knowing what is neural networks?
Great.
It's really interesting.
So there are more applications, right? So maybe classification, maybe pattern recognition, but sort of maybe be a little bit more interesting. And you understand, say, that in the financial market there are some patterns. Specifically, this is interesting, say, in Forex market. For example, let's say I buy Vietnamese dong, I have euros. I buy Vietnamese dong with €1. And then take the Vietnamese dongs and then go buy Australian dollar. And then take the Australian dollars, buy US dollar. And then take the Australian dollar, US dollars and buy what is yen. And then I come back and buy Vietnamese. Sorry, I come back and then buy with my yen, euros. Maybe that I actually find, well, that's sort of some pattern, right? But there are a jungle of returns that you can go on. But that's sort of a loop. I start with €1, go make a round, and then come back. I may make money, right? But I have to find the side. Maybe I shouldn't buy Japanese yen and directly from US I come and buy euro back. Maybe. Or maybe I should do some other sort of round. Right? So some other cycle I use. Right? So that would be some sort of pattern recognition. Or that's actually a graph theory problem, which sort of one can go and then model it with these. Right? Actually, I was still working on these samples, right? Which is very fun and interesting. He's good. Not as good as you. You can do that because you are very proficient with programming. You should just know the method. So I mean that, well, that was one application. There are other applications. Sometimes this is good, sometimes no. But essentially, whenever you have a problem whose solution is very hard, not so linear, then you use this. Okay. If you have a problem that sort of the solution is linear, then you use a linear one. Why should you just go somewhere more complicated? So it's not, I'm not undermining their usefulness. I'm saying sometimes there are better ones. Sometimes there are, but this one, what about better? I'm not saying these are not good. I'm answering your question, your concern again, because it's important, sort of, to understand. We see what we want to do. If it is not linear, then maybe we do that. Yeah? If it is somehow linear model works, then we still with the linear model. So this day, actually, teach officially. Okay? But I think it was a good thing, so that you know a little bit more of those stuff. So if I wanted actually to do multivariate large. Okay, so multivariate large I wanted to do with you. But then time is over. And in the afternoon we don't have any classes to. So then you go home and enjoy yourself. Tonight, or tomorrow morning, somehow check the assignments. I will update them. So I will add a few more. Such that if you have time over weekend, you said you want to go to Danak or somewhere. Maybe when you are on the beach, then you take a piece of paper and then do some derivations. Thank you very much. Oh, you got it.